Okay, let's kick off. So, welcome everybody. Thank you for joining. This is the August 2024 webinar, and due to a last-minute schedule change, we have decided to kind of do a Ask Us Any Questions. Ask me, Oliver, the CEO and founder of Impossible Metals, and Becky, who is our sustainability manager. So what we're going to do is have a Q&A and talk about any questions that you want to answer. I'll cover kind of the technology, the business, and Becky will focus on our stakeholder outreach and environmental side of things. To start with, I wanted to kind of highlight a little bit of like, why are we here? You know, why did we start this company? Why are we focused on this? And, you know, the more I kind of think about this, you know, we have this challenge. I'm kind of describing it as the inconvenient dilemma. I think everyone will be very familiar with Al Gore's Inconvenient Truth that really, I think, shined a light on the climate crisis. And I think what a lot of people are beginning to realize is that this transition away from fossil fuels to electrification, to clean energy, it actually needs massive amounts of minerals, because metals are used to either store the electricity in the form of a battery or to move the electricity in the form of wiring or infrastructure. And so there's now lots of data out there that shows we need 500% more mining to actually deliver this. And of course, there are people that talk about, well, we could reduce demand, we could recycle more, we could have substitutions, and these are all good. We should try to do this. But again, if you dig into the data, for instance, the IEA is saying that just 3% of nickel is likely to come from recycled or second sources in 2030. The problem is there isn't enough material in circulation at the end of life to move the needle. So we can dig into this if there are questions on it. But fundamentally, our belief is that despite best efforts, we're going to need a massive increase in mining. And so now it comes down to the fact of where to get that material from. And historically, we dig holes or tunnels in the earth, we remove material, and we do land-based mining, and that has worked for a long time. But there are increasing challenges these days. You know, one of the biggest challenges is just economics. All the good stuff that we mine, good meaning local, we don't need to build a lot of infrastructure, or high grade or multiple metals, that's becoming more and more challenging because it's already being exploited. So we have to go to further and further remote locations. We have to look for countries that are harder to work with, and we end up with regions where the actual grade is pretty low. And so the economics of these new land-based mines, because the grade, because the location is really expensive. So that's one problem. The second problem is the time. There's been some data published that I think it now averages something like 18 years to get through all the regulatory hurdles, to build all the infrastructure. Nobody wants a mine in their backyard. So it just takes a really long time to get stuff out. The third is the environmental side. These mines, if we talk about nickel, the vast majority are in Indonesia, and unfortunately they're right below the rainforest. So you have to deforest huge areas, and that causes massive loss of biodiversity, biomass. And then if we talk about the next problem, and that's the social impacts. And personally, I don't think this gets enough. Often these mine locations on land are on indigenous lands, or people where indigenous people have lived for many years. And unfortunately, there tends to sometimes be corruption in Africa and other places where, you know, people are able to be bribed, and then suddenly soldiers turn up and people are forced off their land. This happens. There's also a lot of illegal mining where even though there should be rules that go through, but people just bribe, and suddenly mining happens even without any official license. And then, of course, there is the actual child mining and artisanal mining and people mining that is very common in Africa, where people are actually digging tunnels by hand and mining. And of course, there are injuries and deaths. And then, of course, there's all the toxic waste that gets released, because to process these metals, you typically need very strong acid, and you also often use a lot of energy. So you have carbon emissions from diesel or coal, but then you have sulfuric acid and other reagents that don't dissipate. They have to be stored in what's called tailing dams or dry stacked, and often there are seismic activities, and sometimes these dams fail, and there are massive disasters where hundreds of people are killed, as what happened in South America a few years ago. And so that's part of the problem. And then the final problem, I would say, is the fact that we have consolidation around the supply chain, where China has been very strategic and now owns a vast majority of these mines in Africa and in Indonesia, and now has something like 70% of the supply chain. And that's worrying for Europe, for North America. We need diversity. We don't want to be subject to anyone. So there's the geopolitical angle. So those are really all of the problems. I believe, and I think everyone in Impossible Metals believes, that with new technology, we can harvest the seabed in a way that preserves the habitat by using AI and actually mitigate basically all of those problems. We can do it for less cost. We can preserve the habitat. There are no people involved. And so, and there would be a diversity, because this is not controlled by just one country. And so that is why we're here. And we think new technology has a massive impact on the end result. And so that's what we're doing. So finally, before I open up to questions, so please get ready with questions. You're welcome to just unmute yourself and come online. Maybe we can use the raise hand feature. So just use the little hand, which is in the bottom, and then we'll call upon you. And if you prefer, you could also type into the chat. So final thing, we have actually done quite a lot of work on trying to put our story out there and provide data. And so we recently, just a couple of weeks ago, published an FAQ. It's right on our homepage, impossiblemetals.com. It has 4 sections. We talk about the market, like why do we need these? We talk about how can we do environmentally and socially responsible deep sea mining. We talk about the regulations. We talk about our technology, and then a little bit on our company. So that's been published. We also have a fairly active blog post. We recently wrote a little bit about the dark oxygen paper. We're excited to see that science, and unlike others, we don't feel it needs to be attacked. We think we need more research like that, and need to see more. And I think it reiterates that scientists are very critical in this, and the fact that our technology selectively harvests means that we are still going to preserve the habitat. We don't completely destroy it all. So with that, anyone would like to ask any questions to either me or Becky, please raise your hand and we will call on you. So Sean, please go ahead.
Yeah, so currently I can find a lot of information about your Eureka vehicle, but so there's a lot of information about like how you're gonna collect the rocks, but then what is your process for getting them onto a ship, and what does that ship look like, and how does it get from the ship to the shore?
Yeah, great questions. So one of the, I think, innovations that we're bringing is that we're not attempting to have a dedicated production support vessel, which is how the dredger, tractor, and riser pump system works. So we will use existing bulk carriers. Could it be containerized ships? That's a decision that we will fine-tune in the future. But basically, we will use an existing bulk transport ship, and we will retrofit our own crane So the technical slogan is Launch and Recovery System. So this is a traditional crane, but it has some innovation on it that allows it to automatically dock with the Eureka robots. And in fact, that docking happens below the splash zone. So it can actually happen in quite rough weather. And the idea here is that both Eureka and the automated crane communicate both acoustically and optically, and they actually then dock below the splash zone. And then once they are docked, the crane lifts the Eureka onto the ship. Once it's on the ship, we empty its payload, we swap its battery, we do any maintenance that's required, and then we relaunch the Eureka back into the ocean using the crane. And so the key is the speed that we can do that, and that's why we've invented this automated launch and recovery system. We have filed a patent, a provisional patent on it, and the goal is that a Eureka-free system could be reused in less than 4 hours. So that's the total mission time, including launching the vehicle, diving into the deep ocean, harvesting, surfacing, being recovered, battery swap, maintenance, and payload empty. And all of that will happen in under 4 hours where it can be reused. So the simple answer is we're reusing existing ships, but we are installing a unique custom crane automation technology. Does that answer the question, Sean?
Yeah, that answers it pretty well. Thank you.
Great. Just looking at the queue, raised hand. So Kieran is next.
Thank you, Oliver, for affording this opportunity. I was wondering what might be the plan on the part of Impossible Metal to interact with the new leadership at the International Seabed Authority.
Yeah, I mean, we're encouraged to see the change. I think it was a very clear mandate, over 70% of the votes, and you know, we as a small company, we haven't had any opportunity yet to have interactions with the Secretary General elect. I hope we will in the future. But you know, our view is that the Secretary General is very much an administrator. They're not really the policy makers. That is the council and the LTC. You know, as I said, we have not yet met her. We've read with interest what she said, and are very encouraged that, you know, she's on record of saying that the priority is to get the rules and regulations complete, and for them to be strict and robust, and that's exactly what we would like to see. So no formal interactions yet. Hope to have those in the future.
Thank you. Yeah.
Okay, so Ray, I think you're next on the list.
Okay, thank you. What's the time frame, do you think, between when the seabed mining actually takes place and the refined product to cost less than land-based product?
So the time frame, like when do you think we could get into production? Is that kind of the question there?
I'm sorry?
Is the question like when would we be in production? Like what's the best case scenario that metals would?
Yes, that would be one question. Another is, once the production begins, will it automatically, the final product, the refined product, cost less per kilogram than land-based? Is it sort of, or does it have to scale up to a certain point before it comes a lower price point?
Yeah, great question. So time frame, you know, we are working through partners. So today we don't have any exploration permits ourselves, so we're dependent on working through partners, and of course regulations being adopted and exploitation requests being granted. So that's the caveat. That being said, we believe our technology could scale and be ready in around 2027. So assuming those other criteria are met, of course, we need to raise capital to be able to build out the fleet. We need to finish testing, but 2027 is the best case scenario for our technology. On the cost, so the sell price isn't really under our control primarily. It's a commodity. You can go to the London Metal Exchange, for instance, and you can see the commodity pricing that is the daily price. So, and that fluctuates. And of course, people will sometimes enter into longer term agreements. They may discount. What's under our control is our cost. And right now, there are many mines in Australia and some in Canada that are going into what's called care and maintenance. So this is where a mine that is producing, its cost to get the material out of the ground and processed is higher than the sell price, the commodity price. And so the mining industry puts the mine into care and maintenance. They basically mothball it, and they wait until the price goes up because they lose money. What's great about deep sea mining, and specifically our technology, is that we believe we will be at the lowest cost of any new mine. And that's driven by the fact that we have a very high grade resource. The nickel equivalent grade is around 3.2% in the Clarendon-Clipperton zone. We have the 4 metals in one that contributes to that. We also, in general, don't need to build infrastructure. On land, these new mines are very remote. So you end up having to build a road, a highway, a power plant, a village for the workers. All of this adds cost. So we published, and there's a webinar on our techno-economic model that shows that we are significantly lower cost. Now, compare it to land-based mining. Now, if you compare us to the dredging tractors and riser systems that everyone else is using, we also believe in time we will be about half the cost. And the reason for that is to do with the fact that A, we don't need a production support vessel. The other architecture needs this dedicated big ship that is where their dredging tractor is launched from. It's where the riser system goes into. It's where the dewatering is performed. All of that is really expensive. And in our architecture, we don't have that. They also have to do ship-to-ship transfer. So every few days, they have to move the temporary storage of nodules from the production support vessel to a transport ship. And that is yet to be proven. It's going to be expensive. They need a lot of energy and fuel to keep the ships very still with DP technology. They also have single points of failure. So if their dredger collector tractor fails, it will be very expensive and take a long time to recover. If the riser system fails, the whole system stops. The dewatering fails, the ship-to-ship transfer. Our architecture is a parallel architecture with redundancy. So when we've done our economic model, in time, with a very large fleet of vehicles, we can get to close to $100 a ton cost. That's what it costs us to get a ton of nodules to shore. Today, I think they're coming in at around 200. So that's ultimately where we think we can get to. Now, Eureka 3 is not the full size. Eureka 3 will come in about, I think, $160, $170 a ton. But Eureka 4, which will be an even larger vehicle, will lower that cost even further.
Thanks.
Okay. Do we have anyone else? Yeah, I can see Ashmole Productions. I don't know. Please ask your question.
Sorry, that was my email thing. My name is James Cohagen, and my interest is more in the mineral processing side. So, having attended the Underwater Marine Minerals Conference previously, I saw your presentation on bioextraction, and I was wondering if there had been any further developments on that. I'd previously been in contact with your department with Kenneth Bolster, but I see as he is no longer employed at Impossible Metals, I no longer have any access to that.
Yeah, so as you know, we have been incubating a novel approach to refining, actually using live bacteria. We formally spun that out into a new company. So the technology is continuing, but is now called Viridian Biometals. If you want to drop me a note, I can give you the new email address of the people. We've hired a new CEO, Eric Manis, who is leading that activity. He's raised some additional funding, and that we continue to be a shareholder, but a minority shareholder. And so we're excited to see that technology progressing. We're encouraging them to maybe do a webinar, so we'll see if we can make that happen with Eric to kind of give an update. But the tech is continuing. Now, as Impossible Metals, we would love to use their technology, but of course it needs to scale and it takes time. So it's likely that if the 2027 timeframe, that we would have to use an existing tolling relationship with one of the existing refining companies. But we're very, very keen to see this Viridian technology develop and progress, because we think it will have much better energy use, and it won't have reagents. So that's kind of the summary of that technology.
Thank you. That was very informative.
Great. So next I see John S. And please do think about questions for Becky on the environmental side. There's a really good FAQ question that Becky wrote, which was like, what are the impacts of deep sea mining? How are we trying to mitigate them? And so I think that would be a good thing. But please, maybe we lost John.
Thank you for taking my question. Just recently, this whole thing of quote unquote dark oxygen has come up, with oxygen, believed to be evolving from an electrochemical cell on the nodules. And that seems to be a big sticking point for this. To me, it's a little bit confusing. It's like, well, okay, but how is it that the cell isn't being consumed? I mean, these things have been down there for millions of years, and it's like, is this really what's going on? I'll let you go ahead and answer.
So I think Becky would be the best person to answer this. She did write a short blog post on it as well. Please, Becky.
Yeah, hi John. Thanks for your question. Obviously, this is a big topic right now. And Andrew Sweetman, who is one of the authors, was actually in a scientific roundtable I ran yesterday. So of course, all the other scientists there were busy looking to pick his brain on this topic. But essentially, Andrew got results showing that within a box. So if you put a box down on the seafloor and enclose it, what you would expect to see is that oxygen would go down, because the understanding is that oxygen comes from big deep water currents that are coming from the poles. So when you put a box down, the oxygen should go down. So he kept getting results where the oxygen was going up. And he kept getting he kept thinking there was something wrong with the instruments. And he kept sending them to get verified, and everything was fine. So he has these results. They're real results, but they do seem to be counter to the results that other people have gotten at the deep sea floor using a similar or using the same kind of instrument. So essentially, the response is, it's really cool that this has been found, but what does it mean when there's a whole bunch of other scientists who have the same data? Our perspective is interesting. I think that we just need more study on this. So, and that seems to be the general scientific response too. It's interesting, but it doesn't corroborate with other findings with using the same type of equipment, and it needs more study. But there was a lot of different folks who were working on that study together from all different countries and agencies and backgrounds. So the data is real. We're just not sure. Honestly, it's just unsure what it's really showing. Now, what I think the most important part of this conversation is that has been completely lost is the conversation around independence of scientific work being done on behalf of these companies. So the metals company sponsored this work, and there is sort of this criticism that comes across, particularly from some NGOs that are saying, well, if companies are paying for the scientific work, it can't be independent. So what this has really shown, more than anything, I think, is the fact that this work is truly independent, because this paper came out and the metals company who paid for the work has now come out with working to refute that by pointing out the other studies that have been done. So the metals company is speaking, is providing evidence opposite to what the scientists who did the work on their behalf is saying. So I think that's a really important point here, beyond just the topic of dark oxygen, is that the work being carried out by these scientists on behalf of mining companies is really independent, and they do have the opportunity to publish independently.
Right, because TMC didn't suppress it. I
No.
mean, but it's just strange to me, because it's like, okay, it's like, okay, I've created this battery, well, it should be consumed. And
Right.
and if in fact this is really going on, could you backfill with some low cost material, dissimilar metals that would carry the process on? I mean, you reclaim strip mines. I don't think this should be a showstopper. I think what you folks are exploring and pointing out, what Oliver said to open this, is absolutely true. It's like, really, you want to scrape off a rainforest, and you just look at all the other things. It's like, come on, guys, this is a better way to go.
Yeah, thanks, John. We completely agree. And the other thing I would point out with the paper is that this science is expensive. You have to have ships on the ocean, you have to expensive equipment, and the only reason it's getting done is because it's being funded by people that have exploration contracts, and the reason they're doing it is because it's mandated. You have to understand the environment and the baseline. And so, if the call for the moratorium was successful, the vast majority of this science would not be funded. It wouldn't happen. And so that, I think, is another good reason for why the moratorium, in our view, does not make sense. It is banning a location. It's not banning the negative effects of the mining. It's equivalent to saying no mining in Canada. What you should say is, like, we don't want the environment destroyed, the habitat destroyed, the water polluted, people forced off their land. Let's try to stop the negative outcomes, but let's not just say what is 71% of the surface area of our planet and say no, we can't take. And
Right.
Anyway, we have other people. So thank you, John,
Thanks.
for the question.
I'm going to have to drop off, but thank you so much.
Okay, thank you. Ray, I think you're next.
Okay, I'm sorry. I'm going to wait a couple of minutes. I have a contractor outside mowing, and I can barely hear. So I'll ask a question in a bit again. I'll wait a couple of minutes.
Okay. Kieran.
Thank you. Continuing on what John raised, the issue on this dark oxygen, I was wondering, is there any possibility, at least studying point of view, to integrate oxygen sensor on your underwater vehicle? Because you will be vehicles there, and may offer some insight, just a scientific insight. Is there any possibility of integrating that sensor?
Becky, do you want to have a go at that one?
Yeah, so I do need to look up. We have quite a few sensors on the vehicle. I don't think oxygen is one at this point, but oxygen profilers are used for all kinds of monitoring of test mining, and certainly any planned testing that we would be doing would likely have oxygen profilers. The only issue there is that in order to check the dark oxygen, you really have to have that enclosed system, which is very expensive to deploy and recover. We were talking about it on the call yesterday, and talking about how the oxygen monitoring maybe could feed into that, but the answer was no, and you have to really have that enclosed system. I can't remember what it's called, but so yes, many of these it is included on some monitoring programs, and certainly the ones that Dr. Sweetman is going to be on is certainly going to probably have those. But in terms of just monitoring oxygen on the vehicle, it wouldn't be able to contribute to that discussion, unfortunately, because it's not an enclosed space.
Thank you.
Yeah, you're welcome.
And it probably needs to be down there for a certain amount of time as well.
It does, yeah.
Which is also not the great, because our vehicle will kind of operate and then come back. It doesn't stay, weeks or days on the seabed. So yeah, that's another challenge. Okay, Julian, would you like to go next?
Can you hear me?
Yes.
Yes.
Hi. Thank you for hosting us. I had a question about talking about the environmental protections done towards this project. I was wondering, conventional deep mining methods have talked about this plume that is being deployed, and then like a secondary plume that is the sediments that are being processed. In your vision, are you thinking of eliminating or reducing largely both plumes, or eliminating one of them? I was wondering on your approach to this.
Becky, please go ahead.
Great. Yes, so the name of the game in deep sea mining is plume reduction. It is not the only impact. Certainly there's noise and other impacts, but plume is sort of a big indicator of level of impact, certainly at the seafloor. So the whole architecture of our system has been designed with reducing that as much as possible in mind. So I'm actually going to go over to my to our FAQ so I don't forget anything, because I just wrote it. So I'm going to go over there and make sure, because there's a question about this. So sediment disturbance. In the traditional crawler and riser architecture, the crawler goes along the seafloor. So the first thing that happens is that there's tracks on the seafloor. And so those tracks, they're like a bulldozer track or something like that. Now, there's things where they've tried to make it a little bit more buoyant, so it's not as heavy and things like that. But essentially, those tracks are touching the surface. So that's the first part of sediment disturbance. Our vehicles hover over the seafloor, and the only interaction is the claws picking up the nodules. So that's the first thing. The other thing is that to hover over the seafloor, you would imagine that you would be putting your thrusters downward. But what we're actually doing is the vehicle will be slightly positively buoyant, so that the thrusters actually have to push upward to maintain elevation. So that's how we solve not having thrusters pointing downward in that situation, by being slightly positively buoyant. So now that we're at the seafloor and we're moving along, what is the next source of sediment? The next sort of source of sediment in the traditional crawler infrastructure is when the nodules are pulled into the collector. Now, a lot of this is now done by sort of water jets that loosen the nodules so that it's the sort of minimum amount of sediment that's being collected, but it's still quite a large quantity of sediment that gets pulled into the vehicle with the nodules. At that point, most of the sediment is sort of pushed out the back of the vehicle as the nodules go into the hopper. However, it doesn't get rid of all the sediment, because some of it does get entrained with the nodules and pulled up the riser pipe. So that's the second source, is the sediment that's being collected and moving out the back of the vehicle. The way that we have dealt with that one is by not picking up sediment in the first place. So the claws are intended to pick up as minimal sediment as possible. And that's something that we test in the lab by using different claw configurations. And interestingly, we think that there may be options. It may be beneficial to use different claws in different areas. So the Cook Islands, they're like little teeny round nodules typically. In the CCZ, they're bigger, flatter, more buried. So the sediments are different too. The CCZ sediments, yesterday I had them described to me as peanut butter with yogurt layer on top. And I think in the Cook Islands, it's a little bit different. So that's one of the benefits. So we're pulling up as little as possible. Now, there will be sediments that are clinging to the nodule because, like I said, they're described to us as sticky. So we'll be looking at how we can remove as much of that as possible. That design is ongoing right now, whether it's through brushes or other ways of really trying to get as much sediment off as possible. Okay, so now we've got the sediment, now we've got the nodules on board. Both systems have a little bit of sediment in them. Because of the nature of how the crawlers collect, they will have more sediment on board than we should. The traditional architecture has a riser pipe, so nothing is getting out as the vehicle's moving, as the nodules are moving upward, because they're in the riser pipe. But you're right, once they arrive at the ship, the nodules are further separated from the slurry of water and sediment, and that water and sediment goes down the return pipe back into the water column. They're looking at where in the water column that will be. It seems like the farther down you go, the less impact, because it doesn't spread as far. But that does happen. When our vehicles get full and they go back to the surface, the system is closed. It's not, right now on Eureka 2, it's not fully sealed. We're working with sediment modelers right now, so we're learning about sediment and how and where it's coming from and how much and that sort of thing. But we're looking at, does the system need to be sealed with like gaskets and stuff, or is it okay for it just to be closed? How much would be getting out during that transition back to the surface? So that is an area where we are still working out our sediment to see how much would be flowing through the vehicle. But the intention is for it to be as closed as possible. Now that does mean that we will have some sediment when it gets to the surface, which is another thing that we're working out. Right now, our main focus is on creating as little at the seafloor. That's where our technology drive has been. Disturb as little sediment at the seafloor as possible, so we have as little as possible to deal with as we move up. So really, at this point, we need to get out into the ocean to do more ocean testing to really see what that sediment looks like, so we can continue our innovation, which is what we're working toward right now, is getting out to do that ocean testing. So I know that was a lot of discussion about sediment, but I hope it answered your question, because it is the number one thing that we are innovating on at the moment.
Could I ask just one quick clarification?
Sure.
I understood that you said that once the vehicle is full, it would rise up. By full, you mean that there's no, from what I understand, traditional methods, you have those extraction pipes where the nodules are being vacuumed up. So I think the technology there is different, where the vehicle itself is bringing these nodules back to surface. Is that correct?
Absolutely. Oliver, maybe it's worthwhile to show our video, but yes, these are autonomous underwater vehicles. There is no riser pipe. They collect their full payload and they go back to the surface to be offloaded.
I see. Okay, great. Thank you. Thank you so much for that explanation. That was very clear.
Yeah, you're welcome. And in the chat, there's a link to the video I put.
Thank you.
Yeah, I won't, because I'm sure many people, it's like a 60-second video, that an animation that kind of shows how the whole system works. And the vehicles have batteries on board, lithium-ion batteries, just as like you would have in a Tesla. And that provides the energy that we use in the buoyancy engines. And so buoyancy engines are these spheres that we can pump water in and out of. So when we need to make the vehicle dive, we pump water in, the vehicle is heavier, and so it will sink. When we need the vehicle to rise, we pump water out of these spheres, and then the vehicle becomes lighter and it floats to the surface. So that's the primary propulsion. We do have thrusters for maneuvering, but as Becky said, they are designed to be away from the sediment and are really only used for maneuvering to navigate the vehicle. And just for completeness, we also do have control surfaces, flaps, so we can kind of steer the vehicle as it moves up and down the water column. So that's in the technology. I'm happy to answer any questions on the technology as well, but I see Kieran has raised his hand next, so over to you, Kieran.
Thank you. I'm following up on this sediment issue. And as you know, from fluid mechanics point of view, if you reduce the speed of your AUV and also reduce the speed at which you pick up the nodules, obviously sediments will be less. But then all those things will impact your business model. And I was wondering, what is that compromise you have found? Can you go down by factor of 2 and lose the business case? Or can you go down by, factor of 3? It's okay. Any light on that subject?
I can touch on that. There's another parameter, which is how big is the vehicle and how many arms? Because obviously, a Eureka 2 system has 3 arms, a Eureka 3 will have 16, and a Eureka 4 could have 60. And so it's not only the speed, but it's the size of the arms, the number of arms that has an impact. Right now, we don't believe the amount of sediment disturbance is vastly increased or decreased by the speed. But we have only done basic research on that. We need to do more research actually on real nodule fields in the ocean. But the assumption is that if we are smart around the design of the end effector, the claw, and the movement of the end effector, even if we are moving quite quickly, in the current economic model, we want to be achieving something like 1.5 seconds from seeing the nodule to moving the arm with the claw, picking the nodule and placing it on the internal conveyor. We want to achieve all of that in 1.5 seconds, and that's what the optimistic best case economic model delivers. We have now in the ocean been able to achieve just around 2 seconds. So we have still a bit more optimization to do. That's mainly in software. But from the research that we've done to date, the delta of the speed, like if we went at 0.5 seconds versus, so if we went at, say, 3 seconds versus 1.5, we don't believe it's very material to the amount of sediment that is removed, because we've already optimized how we move the arm and how we actually attach to the nodule. It would have a negative impact if we had to move at half the speed, but we could compensate that by having a bigger machine. So there are some compromises that we can make. So hopefully, Kieran, that answers gives you a high-level answer to how we think about that level of optimization.
Thank you. Yeah.
Okay, Ray.
Okay. Continuing on with the theme of the sediment, the sediment that remains on the nodules when they're collected, is that a significant amount? And is there any other possible use for that sediment so you don't have to return it back to the ocean? Is there any consideration to that? What is the makeup of the sediment? And does it have any other use other than just to put it back from where it came from?
Becky, do you want to have a go at that one?
Sure. In terms of how much sediment is clinging to the nodule, boy, is that the $1 million question. that we would love to have the answer to already, but because we haven't deployed this in the CCZ sediments at this time, we don't know. And there's ways to sort of we've thought about sort of, because I guess there's sort of a way they feel sort of there's like a suction because they've grown within the sediment, right? So do you pop it up first, things like that? So there are things that we're going to be innovating on as we get to do that testing. And as in terms of so the first answer is I don't know. Unfortunately, the second answer regarding what we can do with the sediment, in speaking with at our scientists roundtable yesterday, I asked this question, and their answer was just aim to leave as much sediment behind as possible. That's what you should do. If you're trying to maintain the environment, leave as much sediment as possible at the seafloor. Do not bring it up to the surface. So that's the perspective of scientists. Now, from a business case, I'm less sure about that. These are deep ocean muds. They're about as fine gets in terms of sediments. I know that in some areas, abyssal plain sediments do host rare earth elements, but that would be sort of adding on to the mining that we intend to do. And I'm unsure how that would be perceived within the deep sea mining community or things like that. Maybe Oliver has a better answer on that front.
Yeah, I mean, our strategy, as Becky outlined, is we want to have the least impact on the marine environment as possible. That's what is our strategy, and so we will do as much as we can in the engineering design of the collector to disturb the least amount of sediment and to remove the least amount of sediment from the deep sea bed. And so let me give a little bit more about how we intend to achieve that from an engineering standpoint. So the first is how you design the claw. The technical name is the end effector, the end of the arm. How you move the arm, how you design the arm. How do you physically attach to the nodule? Do you scrape the sediment or do you attach the nodule at the top? All of these have big impacts. And so we will optimize for the least amount of sediment. But there still could be sediment stuck because it is sticky. So the next step is that in our collector design, we have what we call the internal conveyor system. So the actual robotic arm picks and places on what is like a round plate, if you look in the picture of Eureka 2, and then from that plate we have a pipe that takes it up into the internal storage, the hopper. Now in Eureka 2 it's a very simple system. We just kind of suck it up and it goes inside the vehicle, but we are right now looking at designs that could go through a sequence of brushing and potentially even water jets to clean the nodule. So that is how we intend to make sure that the nodule, when it gets into the storage hopper of the vehicle, has the minimum amount of sediment inside it. Because if it has to pass through a brushing system and then maybe even a water jet, we think we can achieve such that what actually gets into the hopper has almost no sediment. That's our intention, and we will attempt to design and test and iterate. The key with engineering is, you have a theory, you design something, you test it, you learn, and then you improve it. And that's what we're committed to doing.
Okay.
Great. Sean, I think you're next on the list.
Yeah. So I guess, how big is your expected battery size, and what do you think your biggest power consumer is? Is it going to be the buoyancy engines? I mean, I'm assuming that's going to be, on the larger end of things, because it's got to pump 600 bar of pressure.
Yeah, it's almost a good trade-off between the buoyancy engine pumps and the actuators for the arms. Both are the high users of energy. The battery on Eureka 2 is 14.4 kilowatt hours. And we haven't finally spec'd the size of Eureka 3, but it's going to be a bit below 200 kilowatt hours is the current thinking. But there's still optimizations going on to do that. And you know, the fact that we have 4 motors per arm, one for each limb plus the claw, that does potentially consume quite a bit of energy, and we also want these to move quite quickly. The buoyancy engines, when moving up or down the water column, will consume a lot of energy. But one of the nice things of a buoyancy engine design is that when you're neutral, you don't use any energy. It's only when you're pumping water in or out. Now, we do need to maintain neutral buoyancy by hovering. And so as we pick up nodules, the vehicle is getting heavier. So we need to displace the equivalent weight by pumping a small amount of water out, but that's relatively small. But in our kind of internal energy spreadsheets, it's almost an equal split over the life of the cycle of the vehicle between the motors and the buoyancy pumps. The rest of the system, you know, we have a hyper-powered NVIDIA, but it's relatively small compared to those others. And obviously thrusters are only used for fine control. Cameras, lights, communication, sensors, these are all of relatively low power consumption.
Okay, thank you. So I guess like the battery size of Eureka 3 being kind of near the 200 kilowatt range, scaling that up to Eureka 4, would that put it at 300, 400, or is like how big is the size difference between those? Are you expecting?
It's about a 2 to 3x in physical size. I don't know if we've actually run the maths of where that goes on pack, but that's a rough idea, yes. So this would not be dissimilar to an electric truck. That's kind of the size of the packs that you have on an electric truck. And if you think about it, Eureka 3 in physical size is about the size of one shipping payload, a 20-foot shipping container. But a Eureka 4 is actually 3 20-foot shipping containers in physical size, because its payload is actually one 20-foot shipping container, 25 metric tons. That's the actual payload of a Eureka 4. A Eureka 3 is 6 metric tons payload.
Awesome, thank you.
Julian, I think you're next. Or maybe that was a leftover.
Sorry, my microphone was off.
Yeah, no, please go ahead if you have a question.
Yeah, I was wondering if we've talked a relative extent on the sediment on the nodules, and I was wondering if you've considered the biomass on the nodules, meaning the sponges, the other octopus, whatever not that we have yet to uncover down there, as in like what are your thoughts there? Pre-sweep or like a camera, and how do you plan to mitigate those impacts?
Yeah, Becky will have some great answers here, please.
I got all excited to answer this question because I hadn't come up yet. So that is one of our big value propositions, is avoiding target visible life. And I'm using the term target visible life because there is some visible life. We're talking macrofauna, right? So not things that megafauna, not the things that are in the sediment that we can't see, because we can't see them. It's going to be things that are visible. So basically, if you're a human down there and you can see it, the cameras will see it. Eureka 3 has 3 cameras that feed into a computer vision system that then runs AI to understand the nodules. So it's doing 2 main things. It's seeing the nodules and feeding that into the system so that the arms can pick it up. But the other thing that it's doing is it is trained for visible life. So it's really cool. I don't understand a lot of this. Ali is our computer vision guy, and he's like a computer vision genius. And I try to learn from him. So my apologies for my layman's understanding. But essentially, it can identify that as a nodule, that is sediment. So that's the first thing we trained it to do. That's nodule, that's sediment. Now, there's in nodule fields, a lot of time, there's this one thing that's these sponges, and they're not like big sponges that are all fancy. It's like Andrew yesterday called it a gray smear. So it's like these little spots on the nodules, and they're on like almost every nodule in some places. So there will be visible fauna like that we will have to tell the system, that is okay to pick up, because it's on every nodule, and if we exclude that, then we wouldn't pick up anything. So there will be things that we say it's okay to pick that up. That is not what you're looking for fauna to exclude. But anything that's not those things, so it's not sediment, it's not a nodule, and it's not the things we've told it to exclude, we're training it as life that it needs to avoid. So if it sees the life, it creates an exclusion zone around that life, and any nodule within that area is not picked up. So whether it's sitting right on top of the nodule, or it's right beside it, or it's within that exclusion zone, those are avoided. That's one of the main value propositions of our tech. The other thing that we're looking into as we move into the future is having a maximum percentage of nodules that is picked up. So we could say, yes, system, avoid the megafauna that we haven't excluded, and the exclusion zones around them, but also at a maximum pick up 80%. So because we know that the hard surface that the nodules provide is really valuable to the ecosystem and is required there. So that is that's one of the ways that we're really looking to maintain the function of the ecosystem, by not blowing up a whole bunch of sediment that's going to bury them, and leaving behind those big megafauna, because a lot of times they also sort of act as an island for life, by sort of being these big things there, and leaving behind the hard surface that's required for the fauna down there. So I hope that answers your question. It's one of our things that's really exciting.
Yes, thank you. That was very, very, very cool.
Yeah, thanks.
And the 3D animation tries to show that, where the vehicle's detecting life and leaving islands around the nodules. Ray, please go ahead. Yeah.
How would you describe the feedback or interactions in general that environmental groups have provided to date? So is there a lot of pushback or apprehension or interest, or how would you sort of grade it overall?
Becky,
do you want to take a go? I mean, there's scientists, there's NGOs,
Yeah, and I think that's the first thing that I would say, is that there's like sort of like the ocean scientists, the deep ocean scientists, and they all know each other. They're like a big team because they've spent so much time out on the ocean together, right? And then you have sort of environmental and science NGOs, where they may have a perspective of like, deep sea mining requires the most environmental evidence, all these things, but it's comprised of scientists, and but they may have an activist role within like the ISA or something like that to make sure environmental issues are brought forward. And then there are NGOs that are like the true activism groups like Greenpeace. And so the discussion is quite different, obviously, with everyone. So yesterday I held a roundtable with scientists to discuss a test that we are planning in the CCZ. It's quite a ways out, but we're consulting with them early and often to get their perspective on things right away. And the discussions with them are great. They're willing to share their expertise. Basically, from speaking with many of them one-on-one, the general, and of course I'm generalizing here, the general feel I get is, look, I've dedicated my life to the deep ocean. Obviously, if I'm a deep ocean scientist, I don't want to see the deep ocean hurt. But this is really cool, this technology you're trying to make. And if deep sea mining is going to happen, we want it to be in a way that is responsible like this. So that's generally the response I get. Now, from a scientific NGO like the Deep Ocean Stewardship Initiative, for example, DOSI, they go to the ISA and represent scientific views, things like that. They interact with us. I keep up to date with their minerals committee. A representative attended our demo day last year of Eureka 1. So again, it's just sort of the same scientists are part of that as part of the general community. Now, Greenpeace, in particular, once we go to that NGO end, to me, I kind of feel like they don't really know what to do with us. That's the impression I've gotten. And if there's anyone who's part of Greenpeace here in the room, please feel free to correct me if I'm wrong. But of course, they noted that Oliver was at a conference in London. I think we were listed on their site as one of the companies there. We reached out to them to invite them to our demo day, and they didn't end up attending, but we did extend the invitation, and we're always willing to chat. But that hasn't really been taken up so far. But of course, we'll be reaching out at any sort of milestones to make sure that they are consulted along with everyone else, not just Greenpeace, but other NGOs in that space. So I hope that answers your question. I'm focused on interacting with the scientific community for their feedback as we do our technical process, but certainly we haven't had any sort of like big bad situations with anyone. It's been pretty kind. I mean, these are just people.
Okay.
Yeah. So,
Thank you.
Yeah. Thank you, Ray, and thank you everybody for your questions. I think we're at the hour. Unless anybody has any last minute questions.